and start sharing my screen. And let's see. I want to start by sharing the notes. And so Chapter 9 test should be available after class today, and it's due before midnight tomorrow. The test is in Blackboard. You're going to submit your work. There's a separate Dropbox in Blackboard where you can submit your work when you're done with the test. If you don't want to, there's no need to bother typing your answers in. You can just, give me those handwritten pictures. If when you try to upload them to Blackboard, hopefully everything's smooth sailing. If there's something where I can't open it, I'll send you an email. The homework and activities, I was hoping they would have been done over the weekend because I wanted to be able to grade them and get them back to people before they took the test. Last time I looked last night, I had only gotten the homework from 2 folks, and those 2 folks hopefully can look in Blackboard and see their graded homeworks. I did not get a chance to look at the activities yet. I find those I like to grade the whole class set at once. The homework problems will be closer to what you're going to see on that class. I don't want to spend very much time on it because we spent almost the whole last class on it. Does anybody have any last minute questions about the test? If not, we're going to start looking at that next chapter, chapter 10. So in chapter 10, right now the due dates are March 5th. We will revisit that if we need to, because we did take longer on chapter 9 than I had thought. The chapter 10 activities, the activities 2, 3, and 4 are together in a group. For that, you need to show drawings on dot paper. And I'd like to take a minute and show you folks that in, this isn't your class. In Blackboard, I did in the learning modules content, in the handouts, I did put in dot paper. And there's also some isometric dot paper for the homework, not in this chapter, but for another homework. You'll need, but there's dot paper there that you'll need for that. You can just print it out or if you have a way of annotating it digitally, that would work too. Activity 7, you're going to use graph paper to cut out the different squares and see what type of triangles you can make from them. I have to apologize when I uploaded activity 7, if anybody's using the pages that I uploaded in Blackboard, somewhere in the middle of it, there's a random page from activity 6, ignore it. Activity 9, we will do lion's share of together in class. It involves using those geometric solids. Usually I hand out the geometric solids and have the class work on those when we get to the volume formulas. I will do that display for you. And activity 10, show the measurement that you used on the nets, show all of your computation, and use the metric side of the ruler. You're going to find if you use the metric side of the ruler, you're working in decimals. If you use the inch side of the ruler, you're going to have some crazy fractions. The metric side of the ruler and the decimals is going to make your computation much easier. So that having been said, chapter 10 deals with measurement. And the authors of the textbook talk about measurement as being a process. When you look at that process of measurement, you have to decide what you're going to measure. You have to pick a unit. Then you have to take some sort of device and compare it to measure. And then you're going to express your answer in terms of that unit, And so I'd like to, usually at this point in time, there's from an older version of the activity manual, I hand out an activity that's no longer in your manual, and I hand out a class set of tangrams. And so I'd like to, if this works, stop sharing my screen and take this and flip it over, and hopefully, if I can get things lined up, maybe this isn't going to work as easy as I thought. I can show you my set of tangrams, and they're just, you've all seen the square that breaks apart into little pieces. When we look at tangrams, we're going to say that this smallest triangle is our basic unit. And so we're going to consider that our basic unit. And we're going to use it to measure area. And so if I look at this problem that's in front of me, I'm asked to find its area. I'm worried about the space that's within that figure, that trapezoid. And I'm going to use this tangram as my unit of measurement. And so what I wanted to know is I want to know how many of those tangrams, that basic unit, can I fit inside that trapezoid? And as I line them up, see, I think I have to open another set to get one more of them. Can everybody see that that shape would be filled in with 3 of those smallest triangles, or 3 of that unit? And so I would say that that area is 3 tangrams. And so what I did was I decided what I wanted to measure was the area of this. This was my unit. I compared my unit, and then I'd write my answer as being 3 tangrams. If I move and look at, let's look at another one on this next page. I apologize, they're a little bit blurry, but can you folks sort of see enough of the ideas to what we're doing? This time we want to find the area of this unique shape. And so I'm going to take my basic tangram and I'm going to try to cover that area with my tangrams. And do you see how this would have an area of 2 tangrams? And so I'm using my basic unit to measure that. Instead, if I were doing something like measuring length, I might want to measure length in something like inches, and then I'd take a ruler and compare it and make note of how many inches there are. And so isn't that what you do when you go ahead and measure something? I could say I want to, when I woke up in the morning, measure my weight. Well, what I'd want to measure is my weight. The unit would probably be, sadly, in pounds, and I would use that bathroom scale to measure it. But this idea of measurement being a process, deciding what you want to measure, deciding what unit that you're going to use, and then comparing it. All right. Sorry, I changed my ringtone over the weekend to be silly, and that was really obnoxious. I didn't mean to do that. So this idea of measurement being a process, all right. With this measurement process, the one thing that's really important is that you express your measurement in the units used. Label your units. It's really, really, really important that units are labeled. Have any of you heard the story? I think just this past week, wasn't there a rover that landed on Mars? Have any of you heard the story with the first Mars rover that NASA put up many, many years ago? It got up there, it flew up, it was ready to land. And when it went through the atmosphere of Mars, what happened was it exploded. And over time, when the engineers were trying to figure out what happened, what went wrong, they realized that of all things, the rover had been designed in one system of measurement. And I have to apologize, I can't remember if it was designed in inches and they built it in centimeters, or if it was designed in metrics and they built it with a regular inches feet ruler instead. But anyways, it was built because it wasn't labeled correctly. It was built in the wrong units, and that was why it exploded. And so it's really, really important when you do anything with measurement that you label your units. Okay? Have any of you heard that story before? Can you guys hear me?
Yeah, we hear you.
Okay. Have you heard that story before?
No.
I first heard that story from? I first heard that story from my brother, who is an engineer at Lockheed Martin, who was, somewhat involved in the project. So it's kind of crazy. It's just really, really important that you label those units. So when we look at units, you're expected to know maybe not quite all of this table, but a large portion of it. Hopefully everybody is familiar with the relationship between inches and feet. Does everybody remember that 1 foot is 12 inches? In the same way, does everybody remember that 1 yard is 3 feet? I'm not going to hold you responsible for rods and furlongs because those aren't used very frequently, but I am going to hold you responsible for feet in a mile. Are you folks familiar with the fact that 1 mile is 5,280 feet? Is that a conversion fact that you know?
Yes.
Yes. Okay. Did I ever give you guys my silly way of remembering that? Did I ever? No? Because that was one of those conversion facts that I knew I was supposed to know, but I had a Teflon memory with, and I could never remember it. So I was at a math conference once. It was something put together by a Texas Instruments salesperson. And as she was going through, she was like, everybody remembers that, how many feet in a mile? And she said 5 tomatoes. And I was like, 5 tomatoes? What's that? 5280. 5280, 5 tomatoes. And after I saw that, I never forgot it again. So if it helps, there's a silly way of remembering feet in a mile. So you're expected to be familiar with these units of length. I think the next page that we're going to, I want to hold off for a minute. It deals with units of area. And I'd like to do a little bit of doodling on scrap paper before we get there. So if I look at units of area, well, when I'm looking at area, I'm covering up a space. And so like that tangram covered up a space. My basic unit here is going to be 1 square inch. And it would be something that would be 1 inch on each side. And so then my next one, and I have to apologize, my drawings are not going to be proportionate, would be 1 square foot. And again, I apologize, 1 square inch, 1 square inch, or sometimes you see that as 1 inch squared, that exponent telling me that I'm working with square inches. And so if I have 1 square foot, I want you folks to help me figure out 1 square foot is how many square inches? Any ideas? If this is 1 square foot, this would be 1 foot on this side, 1 foot on this side, and the area would be length times width. Well, that 1 foot is 12 inches, and this 1 foot is 12 inches. And so if I tried 12 inches and 12 inches, wouldn't I have 12 times 12 or 144 square inches in there? And so 1 square foot isn't 12 square inches, but rather 1 square foot will be 12 inches squared or 144 square inches. And when I look at area, I square that unit of length, that conversion fact of length. So if I had something that was 1 yard by 1 yard, it would be 1 square yard. And if I wanted to change it into square feet, well, I'd have to think if 1 yard is 3 feet, 1 yard squared would be 3 feet by 3 feet or 9 square feet. Does that make sense that when I go from length to area, I'd have to square, because I'm squaring my units, I'd have to square my conversion fact. Does that make sense, folks?
Kind of.
So if we think of this as being 1 yard by 1 yard, it would be 3 feet by 3 feet. And so when I multiply it, it would be 3 by 3 or 9 square feet.
Don't you do 4 though? Because it has 4 sides.
Oh no, area is just length times width, right? I think you're thinking of the perimeter distance around. I'm thinking about the area, the space inside.
Okay.
Okay. Thank you for clarifying. So when I get to units of area in the customary system, a square foot is 144 square inches. A square yard is 9 square feet. So for area, conversion facts, I have to square the conversion unit for length. And so a square mile would be, this would be that 5280 squared. One unit though that I'm going to ask that you remember is an acre. And what you need to remember is that 1 square mile is 640 acres. And so that would be units for area. Again, if I'm looking at area, I want to compare areas. I want to see how many it would take to square inches or whatever it would take to cover it. Now, instead of area, if I wanted to look at, I'm going back to my scrap paper, volume. Well, if I have 1 cubic inch, it would be like a little block, a little cube, that's 1 inch on each side. So it'd be 1 inch by 1 inch by, this would be 1 inch. And you need to remember that volume is length times width times height. And so if I wanted 1 cubic foot, and I wanted to know how many cubic inches are in there. And again, for cubic, we'd use that exponent of 3. Well, this would be 12 inches. Length, width would be 12 inches, and height would be 12 inches. So wouldn't that be 12 times 12 times 12, which when we go ahead and multiply that out, we would get 1,728 cubic inches. And the idea that for volume, we'd have to cube that conversion fact. So for example, if I had a cubic yard, well, 1 yard cubed, well, a yard is 3 feet. And when I cube that, 3 times 3 times 3, I get 27 cubic feet. So 1 cubic yard is 27 cubic feet. And so when I go to volume, I have to cube that unit of measurement. So volume, we cube the conversion fact for length. And so rather than necessarily memorizing those numbers, I remember for 1 cubic foot, I'm going to take that 12 inches in each foot and cube it. And that's where the 1728 cubic inches comes from. And for 1 cubic yard, I'm going to take that, it's a cube 3 feet on each side, and cube that to get 27 cubic feet. And again, the fact that that unit is measured with an exponent of 3 to go into 3 dimensions to be cubic helps me remember that I have to cube the conversion fact. So far, so good. And again, this is that customary system that we use: inches, feet, yards. And this customary system that we use is sort of a pain in the backside, because if I start looking at capacity, hopefully everybody's familiar with the relationship between a quart and a gallon. A gallon is 4 quarts. I don't know if anybody's familiar with the relationship between a quart and a cup. A quart is 4 cups. A cup is 8 fluid ounces. A tablespoon is a half a fluid ounce. I don't know, does anybody cook? The one that I always kind of help to remember when it starts getting involved with tablespoons is that 8 tablespoons is a half a cup. And I remember that because I look at that stick of butter that's broken into 8 tablespoons, and a stick of butter is a half a cup. 1 tablespoon is 3 teaspoons. And one that's not here is a pint. Is anybody familiar with a pint being 2 cups? But we've got all of these gallons and quarts and ounces and cups for volume. And it's annoying. I'm gonna skip. Did I miss it? Wait.
No, wait to the next one.
Next one, did I have a separate table for weight, or did I not put that in here?
The next one is dela or kilo, hecto, deca.
The metrics. What I didn't put in here, I guess I'm gonna put it on the side. Weight in customary. When you weigh something, we weigh it in ounces. We weigh it in pounds. I'm abbreviating and I need to write the words out. And tons. Ounces are abbreviated OZ. Pounds are abbreviated LB. I don't know if there's an abbreviation for tons. I've always seen it written out. Does anybody know the relationship between those? Does anybody know how many ounces are in a pound?
Isn't it 16?
Yep. So 1 pound is 16 ounces. And does anybody know how many pounds are in a ton? Anybody?
2,000?
Yeah, it's 2,000 pounds. And so if I look at this customary system that we're using, does anybody notice that there's a whole bunch of conversion facts we're supposed to know? 16 ounces in a pound, 2,000 pounds in a ton, 32 ounces in a quart, 4 cups, a gallon is 128 ounces. Going back, to measurement, inches, feet, yards, miles. There's so many different conversion factors, yes?
Mhm.
Instead, if we were to look at the metric system, we have these prefixes: kilo, hecto, deca, num for the basic unit, deci, centi, milli. And in the metric system, you don't need to remember all sorts of conversion factors because they're all based on powers of 10. And so if I'm only looking at powers of 10, I'm only moving my decimal point, right? If I multiply by 10, I move it to the right. If I divide by 10, I move it to the left. And so in terms of working with conversions within the metric system, I'm just changing multiplying or dividing by different powers of 10, which moves the decimal point. And so back a million years ago, when I used to teach basic math, long before Regents were required for everybody at Peekskill High School, there were silly sentences that people would use. The one that I remember was King Henry died while drinking, chocolate, milk. And I didn't necessarily need the words, but just the first letters. King Henry died while drinking chocolate milk. The K is for my kilo. The H is for my hecto. The D is for my deca. The W is my basic unit. This D is for deci. This C is for centi. And this C is for milli. And when I convert, I'm just moving decimal places. And so, for example, if I were looking at length, the basic unit is a meter. And so if I wanted to say 2.3 centimeters is how many meters, I would go up to my chart with the abbreviations. And when I'm going from centimeters to the basic unit meters, I'm moving over 2 places, 2 powers of 10. And so I would say, okay, that means I'm moving my decimal point 2 places, and I get 0.023 meters. And when you work within that metric system, you're really just moving the decimal point. And if you can remember the correct order for your prefixes, those are your powers of 10. And so they tell you how many places to move. And I don't know about you, but if I were going to try to change kilometers to meters, I would find that much easier than changing miles to feet and using that 5,280. Is this something you folks have seen before?
Yes.
So when I'm converting within that metric system, I just move my decimal point back and forth, whether I'm doing it for length with meters, weight with grams, volume capacity with liters. And so you do have to remember, though, that when I look at area, just like with regular area, you have to square your conversion. And so, for example, if 1 meter is 100 centimeters, 1 meter squared would be that 100 centimeters squared. And when I square 100, 100 times 100 would give me 10,000 meters, square centimeters in a square meter, and so on. And with volumes, you would have to cube it. Although when we look at volume, we talk about the liter. And I'm not going to necessarily hold you accountable for this information, but there is a homework question that asks you to make use of the information. Because if I were to compare ounces to inches, where did an ounce come from? For that matter, how ounce weight wise versus ounce fluid wise, how do they compare? Within the metric system, they do compare. So that if I look at a liter is the volume of 1,000 cubic centimeters. And here's those weight ones. A kilogram is defined as the weight of 1 liter of water. And so within those metric systems, all of those units are based on those powers of 10, and there's a logical way of comparing them. So I know that a million years ago, When I was in high school, there was a big push for America to go to metrics. And it was around the time that Canada went to metrics. Canada wasn't always metrics. They used to be that customary unit that we use. And when Canada changed to metrics, there was a push for America to change to metrics, but Congress wouldn't pass it. And I keep thinking, the metric system is so much easier to work with, being it's all based on powers of 10. But I digress. So in order to convert, we use something that's called dimensional analysis. And when I look at this idea of dimensional analysis, what I want to do is I want to say that I'm going to make a fraction of your conversion facts. So for example, if 1 foot is 12 inches, then I could write 1 foot over 12 inches, or I could write 12 inches over 1 foot. And either way I write it, that would just equal the number 1, because if those two units are equal, when I divide something by its equal, it only gives me the value 1. And I want to set up my conversion facts so that the units, I'm going to say cancel. And so what the heck does that mean? I have here 30 miles per hour, and I want to convert it into feet per second. Well, let's see. I know that 1 mile is 5,280 feet. I need that. Let's see. I need to know something about an hour. What can you tell me about an hour?
There's 60 minutes in an hour.
It's 60 minutes. But I want to change it into seconds. So you have to tell me something more about minutes. 1 minute is
30
Six-
seconds. No, 60 seconds.
Thank you. And so those are my facts. And I'm starting with 30 miles per hour. And when you look at miles per hour, sometimes you see that word per as a slash, which tells me this is a fraction. This is a fraction like 30 miles over 1 hour. Now I want to change my, let's do the time first. I want to change my hours into seconds. So I'm going to take this fact, 1 hour is 60 minutes, and I can either write it as 1 hour over 60 minutes, or I can write it as 60 minutes over 1 hour. We had said that already. With me so far, folks? I want to pick this one because if I write it as 1 hour over 60 minutes, do you see I can think of those words hours as cross-canceling?
Yes.
So that would give me miles per minute. Now I need to change my minutes into seconds. Well, do you see if I take that fact and write it as 1 minute is 60 seconds, that unit of minutes would cancel.
So it would be 20 then, right? Because 30 divides into 60 20 times with a remainder of 20.
We're not doing the arithmetic yet, we're just setting it up. Are you all right with the way I set that fraction up?
Yeah.
I wanted the minutes to cancel. Don't go overboard with the arithmetic yet. And then lastly, I want to change those miles into feet. And I want to replace the miles with the feet. So since the miles is in the numerator here, does it make sense for my conversion fact? I want to put the miles in the denominator. And the word miles would cross cancel. And so what I have left is 30 times 1 times 1 times 5,280 over 60 times 60. And word-wise, what I'd have left is feet over seconds. So that would give me feet per second. With me so far? Now, I would try to do this computation by hand. Is everybody all right? 30 divides into 60 twice. These two numbers, I can divide out the 10. And so now what I've got left is 528 over 2 times 6. So that would be 528 over 12. So if I take that 528 and divide it by 12, let's see, 12 into 52 would be 4. Oh, it's going to give me 44 feet per second. And so do you see how we can use that idea of dimensional analysis, taking our conversion fact and writing it as a fraction, then setting it up so that the units cancel. And it tells me then what I need to multiply and what I need to divide. A course that I used to teach on campus spent a bit of time looking at dimensional analysis, and people would tell me, well, I just know whether to multiply and divide. And if you just know whether to multiply or divide to convert, more power to you. But I've always run into students where, okay, feet to yards, I know the fact is 3, but I can't remember when I multiply by 3 or when I divide by 3. This idea of dimensional analysis to set up your units so that they cross cancel. If it becomes in the denominator, I divide. If it becomes in the numerator, I multiply. Kind of takes the guesswork out of it. I think there's a couple of questions in the homework where they give you some sort of really interesting conversion facts. And I think one asks you to convert a diamond in carats to pounds. And I think there's another one that asks you to convert a metric light year into customary units. So that those are that idea of dimensional analysis. So I'll write with units of measurement and dimensional analysis. Is this something that you folks have seen before? I know a lot of times this idea, concept of dimensional analysis, I know when I look at my own educational career, it was really stressed in science classes much more than in math classes. But it's logical. We're just going to take our conversion fact, our two things that are equal, turn it into a fraction, and set that fraction up so that those units can cross cancel. All right? If there are no questions, that's that first section of chapter 10. The second section of chapter 10 deals with the idea of area. And it's got a couple of statements that are our basic beliefs for the beginning. We say that two regions that have the same size and shape are congruent. That's how we define congruent. Congruent, again, the symbol for congruent. My stylus just stopped working. Here's the other one. Symbol for congruent looks like this. The top is the symbol for similar, which means that they're the same shape. and the bottom is an equal sign. So it means they're the same size. Then the idea that if two regions are congruent, they have the same area. Well, that makes sense, doesn't it? If two things are the same size and the same shape, they'd have the same area. And then this last one says, if a region can be dissected into non-overlapping subregions, its area is equal to the sum of the areas of the subregions. What is that all about? It's like the idea that a whole is the sum of its parts. And so if I had an irregular shape, something like this, and I wanted to find its area, I could divide it into pieces and say that the area of this pentagon is the area of the triangle over the area plus the area of the quadrilateral. And we just want to make sure that when we divide it up, we don't overlap. And so we're going to use that idea to find the area here of this pendulum and the area here of this axe. We're going to go on the idea that the distance between the dots is 1 unit. And so we want to use that idea of dividing things up and maybe rearranging the pieces to find the area of each. So you might wonder how. I'm going to take my pendulum and I'm going to go through these dots. And then I'm going to go through these dots. Everybody with me so far?
Yes.
And now if I look at this little piece here, couldn't I take that little piece and move it over, and wouldn't it fit here perfectly? And in the same way, couldn't I take this little piece and move it down here, and wouldn't it fit perfectly?
Yes.
And so by dissecting it, cutting it into little pieces and moving the pieces around, do you see what I've got now is a rectangle? And just by looking, does everybody see that the rectangle has an area of, well, it would be 2 square units. And so my pendulum would also have an area of 2 square units. There's a couple in the homework where you're given an irregular shape and you're asked to find its area, and you've given some other geometric information around it, or it's drawn on dot paper. And you see how, if you asked me to find the area of that pendulum, I would have looked at you cross-eyed, like, how the heck do you want me to find that? It's all curvy and everything. But you see how by cutting it up and rearranging, it became a much easier figure to find the area of. And the same with this axe. With this axe, if I were to divide it here and here, couldn't I take this little piece and move it to this corner? And couldn't I take this big piece and move it to this corner? And wouldn't the axe also have an area of 2 square units? Interesting? Questions? Well, we're going to take that idea of dissecting figures and use them, which is what you're doing in activities 2, 3, and 4 of chapter 10, to dissect a figure to come up with its area formula. So that I was blessed when I learned a lot of these area formulas. They weren't just handed to me, but I was shown how they worked, which is what we'll be doing. And hopefully that'll help you remember the area formulas for the different figures. And hopefully you'll remember to teach it that way. And it'll help your students remember those area formulas. But I'm looking at the clock and I have to apologize. We've already run over a minute. I'm 2 minutes. Oh my God, I'm so sorry.